Today's lecture will be about rate laws and stoichiometry. In the past lecture, we saw mole balance and design equations for the different reactor types. But if you remember, we assumed that the rate of reaction was basically given as a function of concentration. But now in this lecture, we will define the rate laws that relate the rate of reaction to concentrations first, and then concentrations will be related to the conversion using stoichiometry or stoichiometric tables. And then basically we will have the tools that we need to design our reactors based on the mole balances that we already saw in the previous lecture. So this we will also summarize a bit the previous lecture, so you have a brief overview of what we did there. But mainly we will go through the rate law and stoichiometry, and those will be good tools to not just assume that we have the rate of reaction as a function of conversion, but actually use some expressions for different types of reactions to come to the point where the rate of reaction is a function of conversion. The lecture will be structured just like last time, but before we do that, we will briefly summarize what we learned on the first lecture last week. After that, we will go through the introduction with defining the scope of this lecture and defining also the basic definitions that we will need in this lecture, and then we'll talk about the rate laws as mentioned, and they will give us into some models or how the rate of reaction depends on concentrations, and we will do that through something called power law models, which contain this reaction rate constant, and then we will have specific cases for reversible reactions. And finally, we will talk about stoichiometry, which will take us back to basically what we did last week. If you remember last time, we assumed that we knew the rate of reaction as a function of conversion. And this time, instead of assuming that we have that lab data, we will use stoichiometric tables to achieve the same result. And then once we have that, the design equations from the last lecture will be basically what we need to do to design, be it the volume of a reactor or the time it takes for the reactions to take place in a batch. And then we will end with a summary and class assignment. So reviewing last lecture, we learned that what a chemical reaction engineering is. It's a branch of engineering that combines the study of chemical kinetics with the vessels or the reacting spaces in which these reactions occur. And we learned on why we do chemical engineering, so that why we design reactors, so that reactions can happen with the maximum yield at the lowest cost, so lowest volume or highest time, or fastest time in that sense. And what we did was basically we showed the rate of reaction if we're given that as a function of conversion from a lab data or something, then we can size a reactor based on the mole balance equation and the design equations that we learned. And here are how the different mole balance equations were. First, just as a mole balance equation, so how the moles into the system and out of the system, the accumulation and generation, relate to each other. We said that a batch reactor had a perfectly mixed situation where the concentrations are the same in the space, but we had a variation in time, so it was not a steady state reactor, and therefore our design parameter was time, and that's how we obtain our time. And then for the other flow reactors, we had for the CSDR also perfectly mixed situation where we had no variations in space, but also a steady state condition, and our volume was just an algebraic equation that defines the mode balance equation. Then for PFR and PPR, where we had steady state, but we had changes within the reactor, so we had integral forms for the volume and the weight of catalyst. And we did then do the design equations, because we added the definition of conversion, and we added that into the mole balance, and then we had also this similar relations for the different reactors based on conversion. Then we had a tool, the Levensspiel plot, which we used to design the volume of a reactor given a conversion, specifically for flow reactors, so for CSDR and PFR, and we explained why CSDR gave required bigger volume for the same conversion than a PFR, and where we had the Levensspiel plot areas, the rectangle in the case of CSDR, and the shaded area here, which is the integral so the area under the curve in the case of PFR, where the volumes that we use for designing reactors. So that was basically what we did last week. We defined the different reactor types, we defined mole balance equations, and we related them to conversion rates. And basically what we will do in this lecture is rate laws and stoichiometry, which are the other pillars of the chemical reactor engineering. So in this lecture today we will learn what a rate law is, so basically the power laws, find the rate of reaction as a function of concentration and temperature and other parameters that we will look into. So that's what you will be able to learn. And then we will learn stoichiometry, basically find a concentration as a function of conversion by developing stoichiometric tables. And basically when we combine these two, the rate law and stoichiometry, we will be able to have the rate as a function of conversion, which is basically what we needed to do the design of a reactor based on the mole balance and design equations from last lecture. With that out of the way, we can say a bit about the main basic definitions that we need. A homogeneous reaction is basically a reaction that involves only one phase, so either just a gas or just a liquid or just solids. But here we're mainly referring to only gases or only liquids, basically. But homogeneous is basically we don't have more than one phase in the reaction. Heterogeneous reaction, on the other hand, involves more than one phase, obviously, and the reaction occurs on the interface between phases. This is a typical example for this could be, for example, the presence of a catalyst in a plug flow reactor, or which becomes then packet bed reactor. In that case, for example, you have gases flowing on the catalyst, and the reaction happens in the interface between these two phases. Then an irreversible reaction is a reaction that proceeds in only one direction until the reactants are completely exhausted. In reality, we almost don't have a reaction like this. But some reactions, the equilibrium is so far shifted into the product side that the reaction favors so much the products that we can assume that they are irreversible. On the other hand, a reaction is reversible when it proceeds in either way, depending on the concentrations of reactants and products and other conditions like partial pressure of reactants and so on, and then the relative equilibrium concentrations as well. So, and the molecularity of a reaction is basically the number of atoms, ions, or molecules involved in a reaction step. A reaction is a unimolecular, for example, if it is only one molecule that is participating in the reactions. But this could be, for example, a radioactive decay of some material. It's just the material decaying. A bimolecular is when molecules combine to create a product. Thermomolecular is basically when we have three molecules involved in the reaction, and we're talking about in each step. So yeah. So just like we defined it last time, conversion is moles of A reacted divided by moles of A fed. And in a generic reaction like this, which we will use also today, we used our limiting reactant as a basis for our calculations, which, as mentioned, a limiting reactant is the reactant that depletes the fastest, or the reactant that we run out of the first. And we always use that as our basis for our calculations. And in this reaction, for example, if we assume A is our limiting reactant, then we divide this the coefficients, the stoichiometric coefficients of the reaction with A, and then we can continue our calculations. Now, if you see, we can relate the rates of the different components of the reaction with each other based on these stoichiometric coefficients. You can see that the rate of C, for example, is C divided by A minus RA. So C forms at this rate of disappearance of A. And that's basically just C divided by A, because we don't have here for A. And if we were relating C with D, it would be C divided by D RD. So the reaction rates relate to each other, and we call this relative rate of reaction. And we can, for example, also just put it this way: so the rates divided by their coefficients are equal. For example, if we have this nitrogen monoxide goes to plus oxygen goes to nitrogen dioxide, then the rates of the rates will relate. We just divide the coefficients with with their respective elements, and then we divide the elements, the molecules, with their respective coefficients, and we have this relationship between the different rates of reaction. Now let's define what the power laws, but the power law models look like. A reaction, even though we said it's not the reaction rate, even though we already said in the first lecture that it's not the concentration change in time, but we know that it obviously depends on concentration, and we can relate rate of reaction with concentrations. So we can almost say like that rate of reaction is proportional to concentration, but as with every math equation, in order to remove the proportionality, you would have to add a constant, and this constant in our case is called rate constant, or reaction rate constant K. So K is basically a rate constant that does not depend on concentration, but relates the rate of reaction with concentration. But we will see that K is variable, and it depends on temperature, the chemical properties of the reacting materials, and obviously the pressure and the presence of catalyst and so on. So this rate of reaction usually it must be either found experimentally, or if we find it through rate laws, it must be confirmed through experiments, because there is no way around that. We cannot know how the rate of reaction depends on the concentration of each reactant without measuring the reactions. And the way we measure that is usually we just take the reaction. We take one of the we keep one of the reactants constant, and then we change the concentration of. For example, if we have A plus B goes to C and D, we change the concentration of A and see how the reaction proceeds. If it proceeds the same way, then we will say that the reaction does not depend on the concentrations of A. But if we, for example, double the concentration of A and the reaction rate doubles, then there are one-to-one relationship, so it's first order with respect to A. And then if we actually double the concentration of A and the reaction rate quadruples, then we can see that it's the power of 2 relationship with A. And this way we create this power law model. And we can do the same with B. We keep the concentration of A constant and then see how the reaction rate depends on the concentration of B by changing the concentration of B and monitoring how the reaction proceeds. And that way we can construct a power law. And it will look a bit like this. For example, we have the rate of reaction, the rate of disappearance of A will depend on the concentration of the reactants. And then we have this K, which is the rate constant for the reaction. And then the reaction will be called the order of alpha with respect to A, and order of B with respect to B, to beta with respect to B, and the overall order of the reaction will be alpha plus beta. K is in this case the specific rate of reaction. As you can see, we know concentration is mole per volume, and we know rate of reaction is mole per unit volume per time. So, and since this alpha and B can be whatever number, this the units of K will basically have to change depending on what the order of the reaction is. This is for zero order, where basically it becomes the rate of reaction, because the rate of reaction in this case does not depend on concentration. For the first order, we have the same. We just basically, in order to get the units of Ka, we divide the units of A by units of concentration, and then we only are left with 1/2, and so on. So, and this is the generic unit, but it depends obviously on the order of the reaction.